That's a nice spot to take a nap. I could use some sleep.
Hey, honey. Why, Afiq? Did you hear the sound?
Hear what?
Like someone scream for help.
You are right. But where the sound come from?
There.
Anas, are you alright? Help me please. My leg is getting hit by a log.
Bro, what can we do to help him?
Let's try to pick up this heavy log, Afiq.
Okay.
This is too heavy, bro. Yeah, you're right. Can we try another method? How about we use a moment force, Afiq? But we should find a stick and a huge rock.
Okay, but does it work in real life?
It does.
How are you so sure? Look for me. I found it. This is the stick and this is the rock.
That's good, Afiq. Okay, Afiq. I want to show you that the distance between the pivot point and the apply force could ease us to move this log.
Yeah.
Do you see that?
Yeah, baby!
But Afiq, do you know that when we move this log? Let me show you. I place the pivot at the center of beam. So, we need a more apply force to move this log. Do you see? It's moved a bit.
Hi, I'm going to explain these two lever diagrams and how to calculate the force needed to balance them. In diagram 1, we have a lever with the pivot at point N. The total length of the beam is 8 meters. The first weight is caused by a mass is 60 kilos and the second weight is from a mass is 30 kilos. The distance from the pivot to the weight is half L, which means R equals to 4 meters. So we use the principle of moments, anti-clockwise equals to clockwise. So we write R1 times W1 equals to R2 times F. Both distances are the same. The equations become half L times mg equals to half L times F. The L and half cancel out, so F equals to mg. And then we substitute N mg. And finally, F equals to 588.6 newtons. Now, let's look at diagram 2. This time, the pivot is moved closer to the left side. The distance from pivot to W1 is 1 over 4L. Distance from pivot to F is 3 over 4L. And between the pivot and W2 is also 1 over 4L. We again use the principle of moment. So, R3 times W1 equals to R1 times F plus 1 over 4L times W2. Next, we substitute the values and simplify by cancelling L. And then we rearranging for F, and finally we substitute the masses, and final answer is F equals to 98.1 newtons. Thanks for listening.
Oh, that's cool. But why this happen? Why does it more difficult move when we place the pivot at the center?
Oh, good question. It's happened because when the lever becomes balanced, it's because when the effort arm and the load arm equal in length.
Speaking of that, I realized I once learned in the topic in class. I remember that when the pivot at the center, both sides are equal. So, no side has a longer lever arm to make turning easier.
That's absolutely right.
Furthermore, when we place the pivot close to the load, it will be much easier because of the effect arm becomes much longer than the load arm. If the effort arm is longer, then you can produce a larger turning effect, aka moment with a smaller force.
That's why tools like crowbars and scissors work better than when the pivot is closer to the load. In conclusion, when the effort arm increases, the effort needed is decreased.
Honey, why do I feel like we are forgetting something?
Maybe just your feeling?
Yeah, you're right.
Oh my god, bro.
Bruh.
A'udzu billahi minasyaitonir rajim.
السماء رفعها ووضع الميزان ألا تطغوا في الميزان وأقيموا الوزن بالقسط ولا تخسروا الميزان. From the verse, Allah told us about ever balance, which is, in this verse, it used for measure our deeds. So, I want to relate this physics concept that I use on this video. With imagine, the load is our sins, whereas applied force is our good deeds. Therefore, studying the concept of moment does not only depend on our understanding of physical principle, but also strengthens our faith in the greatness and perfection of Allah, the creator of all balance and order. Thank you for watching.